E is equal to N dphi over dt. N dphi over dt. Now, we define lambda. Lambda is the linkage flux. So this one is defined, as I said, we had all this in the power system, you know. Lambda is N phi. So look at here, if this one had only one term, how much was lambda? Was phi. Lambda and phi, they were the same. Now, when we have an N term, we can replace it with one term, right? We can replace it with the winding one term, but the flux would be N times, right? We can replace this one with this. But this flux would be, let me put it complete at this point over here. So this flux, N phi, this is one term. So these two, if you look at it, they are the same. If you look at this voltage here, this circuit and this circuit, they are the same. We call this one lambda. So basically E is equal to d lambda over dt. You can put a minus sign in front of this equation. They call it Lenz's law. What the Lenz's law said, he said the induced current or voltage, they oppose to the what it caused them, right? It means it's going to generate another current to go cancel what it caused this voltage. This is exactly how transformer works, you know. So, but this is the induced voltage in a winding when it has an N turn. So the induced voltage in the winding is the dphi over dt. Now, so I'm going to replace this one with its electrical circuit, not that circuit. I don't mean that one. Electrical circuit. If you design, if you draw electrical circuit, you are going to have this. This is the L, and we have a voltage here E, right? And this is the current I, right? This is an inductor, right? I'm connecting a voltage and this is the current here, I here. I'm connecting, this part is an inductor. This is an inductor connected to either a voltage source or current source. Just I draw that circuit here, right? So what is E? If I'm going to calculate E. How much is E? Isn't it L di over dt, right? We know this one for inductor. E is equal to L di over dt. Now, let me write it here. I said E is equal to L di over dt. I'm going to put this one, let me see, L. Right, I can put it this way. Hold on. No, I can use that equation, sorry. Let me use this equation. Either we can go this way or we can use that equation. E is equal to d lambda over dt. So this one is going to be d lambda over di times di over dt. And let's bring this equation also in. Also, E was equal to L di over dt, right? This is the Faraday law here, right? E is equal to d lambda over dt. And this is what we know from the electrical circuit, right? For an inductor, E is equal to L di over dt. Compare these two equations. What does it say? This part is the same, right? So basically L d lambda over di. Or you can say delta lambda over delta I, right? Or if the initial of lambda and the initial of I, they are 0, let's put it this way. Continue again. So basically L becomes d lambda over di, or I can say L is equal to delta lambda over delta I, right? Just make it a little bit bigger, instead of d, go to the delta. If lambda 0 is 0 and I0 is 0, right? The initial value is 0, right? So basically I can say L is lambda over I, right? Because delta lambda becomes lambda, right? Because the initial value is 0. Delta I becomes I, right? So this is the L. Now let's go look at this circuit. Now I have the lambda, right? I want to just simplify this equation a little bit. So what was lambda? N phi, right? Over I, right? If I have a circuit, for example, like this. If I have a circuit like this. And I, right? How much is the phi? And then phi over the reluctance, right? For this circuit. So let's replace it over there. So L is going to be n squared, and I'm going to replace this one. N squared I F is equal to, it's very simple equation. If you want to know how much is the inductance of this inductor, say how many turns I have, n squared, right? Divided by the reluctance of this circuit, right? R. So let me replace R with the values we have. It's going to be n squared mu A over L, right? So now you know how to design an inductor. How to design an inductor? What is you can select in the design of an inductor? Number of turns. That's the first thing, right? You can change the number of turns. You can change the inductance value. What does this one say? Mu.
Material.
What type of material to select, right? You can select different type of material. What does it say? These two.
Cross-section.
Physical dimension of the core, right? You can select it. So, for example, you want to design an inductor for a cell phone. Think about it. Cell phone, the thickness is how much? There are lots of inductors inside this cell phone. Look at this one. You cannot go select a core with like a 5 centimeter, for example, length, right? Because you cannot fit it in this one, right? So what do you do? Okay, hey, in every design, everywhere you are going to design something, you have some limitation. You start with those ones to satisfy those limitations first. Those ones, push you. You know what I'm saying? You say, hey, here I have a very, very, very limited space. So I'm going to go design an inductor to satisfy these two first. You know what I'm saying? These two to make sure I can fit it inside this, very, very thin, cell phone, right? Now I'm going to go for the next part. Still, I need, for example, 2 milliamp, right? Still, n is going to be kind of like a physical dimension still, right? Because the number of turns you are putting there, right? If you have to put 1,000 turns, it's going to be difficult to put it there. So you start with this one. You say, okay, now I can fit it inside this cell phone, right? Now I can put up to 500 turns. I'm good, Still I can fit it in. Now I'm going to go select the material to make sure it's going to give me the inductor. So I'm saying every problem the things is different. Once you're going to design a transformer, is going to sit, I don't know, you have seen all these transformer outside. Nobody cares about the size, I mean, if it's like a 10% bigger or smaller, nobody cares, right? So you are open here. So I can be flexible here. So I'm going to go select a cheaper material to make my transformer cheaper, right? Basically, it's going to come to this one, right? So these are all the design parameters you are going to have in your hands based on what you are designing, right? To select which one has the highest priority. I have to satisfy this one or I have to satisfy that one. But this is a simple equation for designing an inductor. when you are designing an inductor, you have all these parameters to play with it to get the number you need. Now let's see how much is the energy stored in this inductor. We're going to see we have a circuit like this, we have a voltage here. I want to know how much energy I need. You know, already you know how much is the energy stored in the inductor? Half of Li square, right? Let's calculate it one more time here, how we can calculate that energy. So we said, in general, we know P, power, is the work done in the unit of time, right? This is definition of power. Or PW is equal to PT, right? So if you make it now differentially, if you're going to look at this one, you can say dW is PDT, right? This is for if the power is constant, easily you can say this one. I have 1 kilowatt all the time, times the time is going to give me the power. But if my power is changing, look at your home. Look at your home. You have a refrigerator, you have a dishwasher, you have a stove, you have lights, those kind of things. These are all power, right? During the day, you can see the power consumption is changing, it's going up and down, right? So basically, if you want to calculate the energy, you use this equation. You say W is integral of P dt, right? So if power is constant, it's easy. You use this equation. But when the power is variable, it does change with the time, so you use this equation. Now I'm going to use this equation to calculate the energy stored in this inductor. So what is power? Instantaneous power. This is the instantaneous power. This is PT. Right? What is PT? That's the voltage times current, right? ET IT. Right? We can replace it over there. But before going there, what was E? You have it somewhere over there. Is a d lambda over dt, right? Or in dphi dt, right? We go with the lambda. It's going to be right. Let's replace this one in that equation. So PET is over there, IT times d lambda t over dt times dt. Now let's get rid of the dt's. I d lambda. I d lambda. So now I'm going to get to physical meaning of it. This is all math here. Look at here, we had this curve. DH, right? That was a DH, right? And if you remember from the power system, the hysteresis loss, remember? When we calculated, we said is the area under the loop times the volume of the core times the frequency, right? Just I'm going to kind of relate this one to this two. How H is going to be related to I? Can somebody tell me? H and I, what's the relation? In general, we said integral H dl is Ni, right? In our case, usually we don't get to the integral. We said sigma HL is Ni, right? Well, let's say we have only one material, not with the air gap. Just I'm going to make it simple, you know. So HL is Ni, right? So H is going to be H is going to be N over Li. N over Li, right? Now let's get to the lambda. I'm going to define here, there are two magnetic curves for every material. Now I'm going to write it here. Lambda and B, I'm going to get the relation. Lambda is equal to what? N phi, right? Phi is what? BA. right? So basically B
BOH.
is going to be lambda over NA. Am I right? So look at here, if I want to change this curve instead of BH to lambda I, right? I can go use this equation and that equation and convert all these things to lambda and I. So this one can go to this curve. I think it was lambda here, I here, and something like this. So my point is when you have the BH curve, we can get to the lambda I curve, right? With these two equations I put it here. So now look at this one. What is the ID lambda? Can somebody tell me? ID lambda. Let's say we go from 0 to lambda 1.
And do into that.
Right? This is the energy. ID lambda. This is the energy stored in the inductor. If the material is linear, this is the one I put it here is not linear. If the material is linear, what is the relation between L and I? If the material is linear,
Lambda into that.
if it's linear material, lambda is equal to Li, right? Somewhere over there we will be.
Sorry.
Should be somewhere here, right? Lambda is equal to N. Now, come back here. W is going to be integral of, I'm going to replace I with what? Lambda over L. The lambda, how much is this one? Lambda over L, or I can say Li squared, right? Just replace lambda with this one, right? So this is the energy stored in the inductor.
How do you come up to this curve, I versus lambda?
From this curve. See, I said H, you can convert it whatever I have, Actually, I should have put it other way. I should say I is equal to L over N times H, you know what I'm saying?
Okay.
You can times this axis by L over N. L is the length of the magnetic circuit, N is the number of turns. So this axis is going to change, convert to I, right? And here also I made a mistake. I should go other way. I should say lambda is equal to NA times B, right? If I times this axis by NA, it's going to convert to what? To lambda, right? So can somebody tell me what's the difference between these two curves? BH and lambda I. If I am a manufacturer building this course, which one I'm going to give you? Which one do you rather to have?
Lambda
Lambda I. There's a lambda I. How many of you are agree with that? Lambda I. You want a lambda I curve or BH curve? So why? Okay.
Physically related to the inductor.
Any other idea? So I'm gonna give you lambda I, but keep it in mind. This one. I'm gonna go sit in my lab. I'm a manufacturer. I design one inductor here, right? And I come up with this lambda. I'll measure the length, turns, and all those kind of things. I say, okay, this is your lambda I. Now, are you gonna use exactly inductor what I have? Most probably not. For example, I designed the one I designed in my lab is 1 millihenry or 2 millihenry, whatever, right? You want 10 millihenry. You want a 0.1 millihenry, right? So you don't want this curve. This curve depends to the physical dimension. This is what you design